Okay, good afternoon, everyone, and welcome to this first of a series of short talks that the Civil and Environmental Engineering Department, I should say, is putting together. Uh, my name is Roberto Leon. I am the Associate Head for Undergraduate Studies, and I'm very glad that this afternoon we have one of our young faculty, Dr. Eric Jacques, who's an expert in blowing up things, and he will be self-introducing himself, and then he's going to plow right into his discussion of the August 4th, 2020 Beirut explosion. So Eric, it's all yours.
Thank you for the kind introduction. Let me tell you, everybody, we're going to have a blast today. Ha ha ha. All right, now that the humor is out of the way. Yeah, well, my name is Eric Jacques. I'm an assistant professor here in structural engineering. We're going to talk about the Beirut explosion that happened, I guess, just over a month ago. And we're going to take a deep dive into sort of what happened, what went wrong, what we observed, and what people here at Virginia Tech, particularly students, both undergraduate and graduate students, are doing in terms of research to try to prevent these kinds of disasters from happening. Let's see here, next slide, there we go. So I think you kind of got the gist of the introduction. So the only thing I might add is that I'm Canadian, so if you hear me say A or talk about Tim Hortons coffee or igloos or hockey, then you have to forgive me. But as was mentioned, I'm a blast protection expert and structural engineer. My work, if it's an applied research, I look at protecting buildings and people and occupants against terrorist attack, accidental explosions. In terms of fundamental research, I look at the development of novel structural concepts and material applications for enhanced survivability and resilience of infrastructure under extreme loads, particularly blast. There's a photo of me and my little guy, Neil. I guess that was a year ago now. He's a bit bigger, but he helps out the lab when he can. And by help, I mean slow things down, but that's okay. He makes cute noises, so it's all good. So what is this talk? Well, this talk is going to go into some of the origins of the August 4th disaster. We're going to talk about what happened. We're going to describe some of the ensuing damage to both the citizens and the city of Beirut and what kind of steps could be taken to protect and rebuild. We're also, as we said, going to highlight some recent research by VT Civil Engineering faculty and students in the area of blast protection of buildings. Kind of give you guys an overview of what you could be doing if you decide to pursue civil engineering, particularly structural engineering and materials. In terms of the contents, so I realize the blast protection is a fairly new field as far as fields go in engineering. So we're going to give an introduction, spend about 10 minutes or so, bring you up to speed on the basics. What is a blast? What's explosive material? What happens when a blast interacts with a building? What happens when blast interacts with people? And then we'll talk about some of the strategies, generally speaking, that we do to try to prevent that. We'll then dive into the explosions, maybe spend about another 10 or 15 minutes just talking about the actual explosion in Beirut itself. We'll talk about damage to buildings after that, and then we'll talk about Virginia Tech research in that area. Starting out with our introduction. We need a level playing field. And so to talk about blasts, to talk about explosions, we need to know what those are. And so an explosion is basically, in other words, just a really rapid release of energy. The energy is released as a big or a large volume change. So that large volume change comes from ideally a very small package, if you will. So explosions can come in a few sources, can come from energetic material. So it could be TNT or some other high explosive that gets consumed through a chemical reaction that makes a massive amount of a large volume or a large pressure at a small volume that expands outwards. It could also come from a vapor cloud. So for example, oil and gas, you release some hydrocarbons into the air. Those hydrocarbons disperse, and if there's an ignition source, it'll detonate and form an explosion. It could also come from a runaway chemical reaction. So you could be in the manufacturing sector and you mix the wrong chemicals and you have a detonation. Another one that you could see could be a pressure vessel rupture. This could be accidental, or it could be a fatigue failure, but maybe you have a vessel that you charge to high pressure and for whatever reason it bursts, you'll get an explosion. And so one of the things that all these sources have together is that they cause an immense amount of damage and casualties. And that's primarily due to the formation of a shock wave. So the shock wave is the really damaging effect. But those shock waves can also be accompanied by, depending on the characteristics of the scenario, projectiles, so flying debris and shrapnel. You could have high temperatures and a fireball. You could have radiation if it's a nuclear blast, although we're not going to focus too much on that in this talk. And you can also have toxic and non-toxic chemical byproducts as well. In terms of the blast threat, that could come from an accidental industrial explosion. It could come from accidental storage of munitions or explosive material. It can also be terrorist attack. I like this quote because I think it's pretty representative. It's primarily meant to stand for terrorist attack, but Frickberg here in 2002 wrote, "Explosions and bombings are the most common deliberate cause of disasters involving large numbers of casualties and destruction of property." And while I agree with that from the terrorist perspective, I would also go one step further and say in terms of man-made disasters, explosive blasts are equally as, are also applicable in that case. So focusing on high explosive, because that's relevant to our discussion today, let's answer the question, what is a high explosive? And a high explosive is a material that undergoes a detonation. And a detonation is basically a chemical reaction that has some pretty specific characteristics. One characteristic of that is that the velocity of that chemical reaction is greater than the speed of sound in the material. So it's an extremely rapid reaction or combustion of high explosive material. Another characteristic of a high explosive is that the chemical process of detonation is not affected by ambient conditions. So the material will detonate just as well underwater, in space, to some extent, on the ground. It could be very humid, very dry, very high temperature, low temperature. It'll go regardless. And the other thing that characterizes a high explosive is that the detonation itself is triggered by a shock, typically a smaller explosion. And so you can't really, theoretically, technically, you can't light a high explosive on fire. It shouldn't detonate. You need to trigger it with a shock. And so when we're talking about shock, it could be a physical shock. You could drop it. I'm sure you've all seen the old time railroad movies. People are holding nitroglycerin, and that's sensitive to shock. Other cases like AMPHO are very stable, and they require a smaller booster charge to get going. When you do have a high explosive material that detonates, the upper limit of energy that can be released is the heat of combustion. It considers the energy released if that material becomes fully oxidized. But there's two steps that are relevant to our discussion today. One is the initial energy that gets liberated during the initial detonation. And so we call that the initial shock. It's the one that forms the initial shock wave. And then you get a secondary energy release that's known as afterburn, and it occurs in the trailing fireball. So usually high explosive materials are under-oxidized, so there's not enough oxygen in the material itself to run the reaction through its entire energy potential. Instead, it detonates, and then you get these partially combusted products that float in the air that consume ambient oxygen and then form a fireball, which has additional energy release on the shock characteristics. So when you have a high explosive event, what does that do to a building, basically? And so we'll use the conceptual case of, let's say, an IED, a terrorist bomb located in this vehicle parked adjacent to a building. That explosion is going to occur inside the vehicle. The high explosive will be converted very quickly into a massive quantity of gas packed in a very small little space. That gas is going to be expanding and push outwards in all directions in a spherical direction. So it'll propagate in all directions in the form of a sphere. If you place an obstacle like a building in front of that structure, what's going to happen is the shock wave is going to expand and portions of it are going to strike the target. The shock front is going to sweep across the sides and around all surfaces and then continue on its path. And you can kind of get that sense right here where the shock front is going to first strike where the distance to the explosion was the smallest, and then it's going to sort of sweep around on all surfaces. Pressure is a three-dimensional force. Even though your shock has a direction, pressure is acting everywhere equally. And so the pressure wave will be always pressing inwards on the building, even as the shock front passes past it. If you were to put a pressure sensor somewhere here, let's say between the source of the blast and the building, you're able to measure the pressure versus time history, you'd get a graph like one that's shown over here on the right. And so initially, at some distance away, let's say the explosion is a little bit off in the distance where I'm pointing. If you detonated that material, you would see a flash of light and the fireball. Maybe you'd see the shock coming towards you, but you wouldn't actually feel the effects of the shock until it arrived at your position. That's because it takes some time to get there. And so the pressure time history, if there was a sensor at your location, would record no pressure until the time when the shock interacted with your body or the sensor, at which time you'd see this instantaneous rise in pressure. And then as the shock front passed your position, the pressure would decay down to zero. Eventually, the pressure would return back to normal conditions. We're talking about milliseconds here, so it's a very fast loading. But because that shock wave has pushed all of the ambient air out of the way as it expands, you're actually left with a suction phase that wants to suck everything back in towards the blast. So the pressure wave that you would feel in an explosion typically is going to have this outward thrust. That's the most powerful. And then you'll kind of have a more muted, longer negative suction phase that pulls everything back in. So it's kind of it's certainly a dynamic load, and it happens in the order of micro or milliseconds, depending on the distance. This is a great video that kind of showcases some of what I'm talking about. So in the middle here, you can see that there is a high explosive material. We've got some pressure sensors that they've had in this experiment just to monitor the pressure. This is a test of a building facade that some colleagues had done. The building facade is purposely designed to be blast resistant, so it's not going to fail. You'll see some damage. But what I want you to look for is look for that shock wave that forms. And you'll notice the shock wave because it kind of interacts and it reflects the light in a funny way, and you'll see it take that hemispherical pattern. So let's go ahead and watch, and I'll narrate as best I can. Right. Detonation. You can see the shock front sweeping across the top of the building. It's not an instantaneous loading. It's very short, but you can still see it passing up over the side of the face of the structure. You can see the windows are all shattered, but they're still intact, so they're still protecting occupants. You can see the suction phase now as the dust is getting pulled back here on the surface. It's getting pulled back towards the source of the detonation. The camera is now vibrated, which means the shock wave is expanded to the position of the camera. And you get a lot of dust and cloud and then the soot from the chemical reaction. I'm going to play it one more time just so you can, again, look for that shock wave, the way it starts from the point of the blast and sweeps across the surface. I think that's really interesting and relevant to what we're talking about. So boom, there you go. See, it's reflecting the light and sweeping across the building. All right, so that's the basic idea of what happens when a blast interacts with a structure. When we talk about protecting buildings against blast, what we want to be doing is achieving several performance objectives. These performance objectives have to do with trying to limit the extent and severity of blast damage in order to minimize or reduce human casualties, when you prevent damage to assets, and we want to allow the emergency evacuation of occupants following a blast event. And so to do that, the three performance objectives that we're trying to design for are limiting structural collapse. We don't want to have any structural collapse if a part of the building comes down, not much left to escape from. We want to make sure that our occupants inside the building are safe. And so to do that, we want to maintain the building envelope as a physical barrier, protecting people and infrastructure and assets that are inside a structure against the damaging effect of the shockwave and fireball and debris on the outside. And then the last thing we want to do is we want to minimize flying debris. So we want to minimize flying debris both inside of the space where the people are at, and also if there is a failure of a window or a wall, make sure there's as little debris as possible that can go and hurt people. And that's evident, I guess. So buildings, pretty robust. We can design them pretty well to resist blast. Blast effects on humans is another matter. We're pretty squishy. We don't do too well against these kinds of loads. And there's really five types of damage that a person or a human may see in a blast event. One is the primary damage that would occur from the blast itself. So injuries that are related to the shock directly. That usually happens when you're very close. The other one is a secondary blast injury that could occur from projectiles that are accelerated by the initial blast directly, so pieces of casing, debris in the surrounding area. A tertiary blast is going to occur from the impact of the person, maybe with the ground, perhaps the impact of the person with debris that's falling or flying. So you start to move away, it's less direct damage. Another one that's in here I've listed is a quaternary Injury, this is any other injury that maybe is pre-existing or exacerbated. This could be injury or illness from the blast. So we're talking about things like a burn, a fire, a crush injury from a building falling on you. It could be asthma, that's asthma or breathing problems from toxic dust, angina, hypertension, these things like that. And the fifth thing to think about when you have a blast disaster, injuries to human, is PTSD. So even if you're physically unharmed, psychologically, you may have long-lasting effects. So those are much harder to protect against than the building side. Right? And so hopefully with that sort of basic sort of understanding of blast, let's dive into the Beirut explosion. And to do that, we need to have a little bit of a background of Lebanon, Beirut, and the port itself. And so Beirut, located in Lebanon, a country sort of straddling or in the Middle East, borders the Mediterranean Sea. It's next to Syria. We've got Israel, Jordan's nearby, Turkey's also nearby, Egypt. So it's a pretty cultural hotspot, let's put it that way. The population of the city of Beirut is 361,000. Directly in the city itself, the metro area is 2.2 million. Space is pretty limited, so it's a very urban city. You can see here's a photo facing, I guess, to the east. This is Beirut, lots of medium and high-rise buildings just tightly packed together. The port is right back over here in this photo, if you can see my cursor, giving you a sense of the current socioeconomic status in Lebanon. Lots of unfortunate wars over the last 100 years or so, and even longer, realistically. Biggest one being the Lebanese Civil War. That's shaped a lot of the current political climate in the country and the surrounding area. That causes a lot of political strife and uncertainty that's going on. There's also major instability and spillover effects from the Syrian Civil War. Lots of refugees and the hardships that come with that. Other major challenges to think about when we talk about this disaster is in March of 2020, the Banque du Liban, the Libyan National Bank, defaulted on some major loans. And so there's a financial crisis going on now as well. And if that's not enough, let's put in COVID-19 on top of that. So lots of things happening in terms of the current status of Lebanon. The last thing that I want to mention is regarding the port of Beirut itself. So I've shown the port down here. So we've got the major port facilities, the cargo terminal, various other terminals, warehouses. The port of Beirut is the main point of entry exit for over 70% of the country's external trade. So it's a massive connection with the rest of the world. And the last thing is the economy of Beirut is primarily service oriented. So Lebanon has some pretty open financial regulations or systems. So banking is really big for the area there, and as well as tourism. So let's talk about the disaster. I think we all know the disaster started in the port. Sometime in the evening of August 4th, 2020, late afternoon, early evening, a fire broke out right here. This is in warehouse 12 in the port of Beirut. I don't want to speculate, but I'm just reporting what was out there. It possibly started by some maintenance workers who were welding on the docks, but really we don't necessarily know. In this building right here, warehouse number 12, there were stored approximately 2,750 metric tons of ANFO, ammonium nitrate. Actually, ANFO is the wrong word. It's ammonium nitrate. Get rid of FO. That's something else. That's my mistake. So for metric tons, this is 1,000 kilograms. So we're talking 3,000 US tons of absolutely phenomenal amount of potential explosive material. And on top of that, an unknown quantity of fireworks. And so somewhere in around 6:30 in the evening, the fire broke out, and the next day, satellite images showed Port of Beirut looking something like this, to give you a feel for what happened. So after the blast, this was the condition of the damage. Thinking of the timeline of the disaster, so we're talking late evening, local time. What started was warehouse fire. So here we got a photo of the fire taken from a video. You can see the billowing smoke going. We don't exactly know what's burning in this fire, but certainly there was some combustible material around that was there to ignite. If you watch the videos closely, you'll see this flash of light here in the screenshot. Those are the fireworks going off. So you could see the fireworks just before the initial blast or the larger blast popping in the air. And then we saw the detonation, so massive red-orange fireball that occurs and basically envelops the whole port. The fireball and detonation causes a shock wave that travels faster than the speed of sound, and it just entirely swept across the entire city, causing massive amounts of damage. Behind the shock wave, there's very humid air. We're near the sea at the time, and so we get this physical phenomenon known as a Wilson cloud that forms. So the cloud that you're seeing isn't actually the shock front, but it's a byproduct of the humid air behind it. This funny red-orange color that's produced in the mushroom cloud that's created, this is nitrogen dioxide, a stinky byproduct, unpleasant smelling gas that occurs after you detonate ammonium nitrate. I think, well, I'm not sure if audio will play. Let's assume it will. If it doesn't, maybe we'll just move on in the interest of time. But I've got some videos here of the detonation. So let's take a look. Let's look carefully, see the fireworks going off. You can see some smaller explosions that are happening, right? Still burning. Detonation. And I'm not sure if you can hear, but you can clearly hear the detonation occur, and you could see the shockwave traveling over the buildings, kicking up roofs, windows, all the kind of debris. There's a huge mushroom cloud, all kinds of dust. Who knows what's in the dust? Just enveloping the city. Very reminiscent of 9/11 almost. What I did, just a little bit of sleuthing. If we assume that the shockwave, the sound of the shockwave travels at the speed of sound in air, if we just listen and we listen for the sound of the blast to when the sound hits the observer, it's about 3.5 seconds. And so I estimate that sound for 3.5 seconds at 343 meters per second, we were about 1.2 kilometers from the source of the blast in this video. Likewise, here's another view sort of from the west facing east of the port. Let's take a look and see what we see. There's the blast. Again, not sure if you can hear, but I count just under 3 seconds, the time it takes for the sound to travel to our position or where the camera is. There it is. You see a shockwave traveling on the water. So in this video, I estimate we're about 1 kilometer from the point of the blast. Right? So absolutely massive explosion occurred. The air pressure shock was felt and heard up to 250 kilometers away in Cyprus and Israel. As you can imagine, when you've got such an enormous quantity of explosive material detonating all at once, it's going to shake the ground, and in fact, it caused a human-induced earthquake. This earthquake was picked up on a series of seismographs in the area. The USGS Community Internet Intensity Map. Also, people went in and recorded empirically what the shaking felt like, and you're left with something that has an intensity of about 7, MMI is 7, which is a fairly strong shaking. The USGS estimates it was a magnitude 3.3 earthquake that blast created. The Geological Survey of Israel, with their seismograph network, you can see the locations here in the vicinity. They recorded the ground shaking on their sensors, and you can see the closest station, Emron, located right here, is about 125 kilometers from Beirut. It took that seismic wave somewhere in and around 10 to 15 seconds to travel that distance. And then you can see there's a delay as the seismic wave travels to all the other stations. And so they estimated, based on those recordings, magnitude 4.5 earthquake. Absolutely enormous blast occurred. So what caused that huge blast? Ammonium nitrate. What is ammonium nitrate? Well, it's a highly soluble salt that's made from ammonium and nitric acids. I've given you the chemical reaction over there. Sorry, 1 second here. Perfect, there we go. Ammonium nitrate is salt, highly soluble in water. It comes in pellets, or they call it prills. You can see the pellets here, these small little particles, these little beads almost. It's primarily used in agriculture as a fertilizer for its high nitrogen content, which is really great. The other major use of it is actually as an ingredient in industrial explosive mixtures, primarily in mining, civil construction, and defense. Again, I've sort of used the words ANFO, which is a mistake. It should be ammonium nitrate. Ammonium nitrate accounts for about 80% of the explosives used in North America. So it's a pretty use in many ways, productive ways, both agriculture and for explosive materials. The thing about ammonium nitrate is that it is hazardous. It's extremely hazardous. And so up here, I've given sort of the hazard rating from the National Fire Protection Association, giving you a sense of what kind of hazards to watch out for. I would summarize them as really three. The first one is fire. So ammonium nitrate on its own does not burn. You can heat it up, and what's going to happen is it's going to melt and decompose, but it itself is not going to burn. It's a chemical that has a lot of oxygen, and so it's a strong oxidizer that accelerates the combustion of other things. So much like you start a fire and you blow on it to make the embers burn brighter, you're forcing oxygen into the fire. Ammonium nitrate does the same thing. So it doesn't burn, but it certainly accelerates existing fires. Ammonium nitrate is very sensitive to decomposition. So for example, if the temperature is very high, if it melts, or if it's subjected to large pressures, or perhaps the wrong humidity, things like that, there'll be exothermic chemical reaction that's going to occur as the material decomposes. That exothermic reaction means giving off heat, and so you increase the explosive detonation sensitivity just because of the change in the chemical properties. If you have suddenly a material that's more sensitive to detonation, there's an increased risk of explosion. So ammonium nitrate can be detonated from a strong initiating charge. So you have to set it off with something else. It needs to be initiated by a shock. And it's usually pretty stable. It's difficult to do that. However, if it starts to decompose, then it can even self-detonate or be much more sensitive to detonation. So we have to be very careful about how we store ammonium nitrate for those very reasons. And there are very strict requirements about how you store and handle ammonium nitrate. Unfortunately, in this case, it doesn't look like any of those requirements were followed. Again, I don't want to get too much into the story of how all this ammonium nitrate ended up there, but it was there for several years, and it's kind of a tragic story, things falling through the gaps, it sounds like. But we do have some photos from inside the warehouse, purported photos. So here's one from Twitter that I got. It looks like these gentlemen at some point or another were fixing some doors, but you get a sense that these bags are not in very good condition. They're dusty. The environment is very humid, and ammonium nitrate absorbs water from the air, which it shouldn't be doing because it accelerates decomposition. Here's another photo of inside. Everything's just stacked haphazardly, poor ventilation, no firewalls. It's just a big pile. It's a mess. It is not what you would be doing with such a dangerous material. And of course, fireworks nearby, it's just absolutely a disaster waiting to happen, and that's exactly what happened. We've seen the videos, so we know what happens. Let's think about where this is in terms of the history of accidental explosions, starting here on the left. This is from Statistica, just a simple graphic that answers the question, how powerful was the explosion in Beirut? Well, they use as the baseline the little boy Hiroshima bombing that had an explosive yield of 15 kilotons of TNT. The Beirut explosion was about 10% of that. So it gives you the size of the explosion. Down here, the 1995 Oklahoma City bombing, where I think it was 2,000 pounds of ammonium nitrate fuel oil, somewhere in that, maybe a little bit more, was 0.002 kilotons of TNT. So the scales here are totally different, right? But still incredible when you think about it. The other thing that is just tragic is this is a case of history repeating itself. This type of explosion, ammonium nitrate, is not new. These disasters have been occurring for the last 100 years. The first one being in Oppau, Germany, a BASF chemical factory where they manufactured ammonium nitrate and they had it outdoors in a huge pile, and it solidified. It decomposed, became a hard rock. And so the workers decided to break up the rock. They would put TNT charges in there and try to break it up with explosives like you would do in mining. Needless to say, that didn't go so well. In the last 20 years, there have been many other ammonium nitrate disasters. One of them that's kind of infamous is in 2001, 10 days after 9/11, in Toulouse, France. There was a giant explosion from ammonium nitrate. Another big one was in 2015 in Tianjin, China, and now Beirut. So it's just a tragic situation of what happens if you're not properly storing and handling these dangerous materials. Damage assessment. So now that we have an understanding of the blast, let's look at some of the damage. So these are some estimates that were put out by Strategy PwC. This is as of August 14th, so this was really quick. They made an assessment of what was happening. They estimate that at the time, as much as 40% of Beirut had been severely damaged, which is a phenomenal part of the city. The entire port basically taken out of commission. Buildings at the time, they were estimating about $5 billion losses of buildings, somewhere between 30 or 40 buildings outright destroyed, 3,400 uninhabitable, and the list just goes on in terms of tragedy and heartbreak. In red are some of the districts that were most hard hit by the disaster. Hospitals very severely damaged. There's many of them in the proximity to downtown. Others with low damage. Schools, places of worship, cultural sites, public infrastructure, just absolutely complete disaster here in Beirut. These figures were pretty early on, so I pulled some out as I guess yesterday or 2 days ago. As of September 7th, at least 190 deaths, 6,500 injuries, 10 to 15 billion dollars of damage. I think that's probably going to go up as time goes on. One of the tragic things about this is right now they're estimating only about $3 billion of that is insured losses. So there's a lot of disparity there in what's available to rebuild. 300,000 people homeless, which is a terrifying number. The other one that comes up is the port stored 85% of Lebanon's strategic supply of cereals, grains and such, and that's entirely gone. Now there's issues about sufficient food for folks, thinking about rebuilding, construction materials that are needed, and just the scale of the disaster is mind-boggling in that sense. So thinking about the damage, starting at the port, we've got some photos here taken from the European Space Imaging. So at the top is a photo before. I think this was somewhere around July 2020, in and around that time period. Down here is after. We're going to get really into the damage, but look at the size of the crater, look at buildings flattened, what was before and after. It's just absolutely a catastrophe. Let's zoom in on some of those port buildings. So these port buildings, as we're going to see, were just warehouses, storage, so just light steel with a light cladding on them for the most part. Those buildings, some of them were entirely flattened. Others had their cladding torn off and their columns and beams all twisted and mangled by the force of the explosion. Also to keep in mind is that massive ground shock. So that massive ground shock would have certainly damaged some of the structures. It's primarily not so much the steel ones, but other heavy concrete and masonry. We'll see some later. That certainly would have caused some huge damages. Here's some more photos from Instagram. This is fantastic with 21st century technology. We can go there without having to go there. Look at this massive crater that was created, 125 meters long, 45 meters deep. Just the scale of it is incredible. Boats were capsized, absolute complete destruction in the immediate vicinity of the port. As we start to push outside of the port, so you can see all these warehouses are down. Take a look at these sea containers. These are probably full. These are extremely heavy. They're very large. They were probably stacked in these areas, and they're thrown in and amongst the neighborhood like children's toys. Turning our attention over here to the even though we're several kilometers away from seeing the buildings, you can clearly tell that their facades are completely obliterated. High hazard failures of windows and other debris. You could imagine the sort of chaos that would be raining down after the blast wave as things were falling from these buildings into the street and also flooding the people's homes and apartments. Another view facing the west, again, more of the same type of destruction. The grain silos breached. All this stuff is not dirt or sand. This is grains. It's incredible. There would have been a tsunami, a local tsunami created by the force of the blast as it made this crater. Here's a boat sitting on the shore now. Turning our attention over to the cityscape again, windows are all blown out. These port, I think they're probably administrative buildings on the port are still standing. That's because they're concrete construction, but they're still seeing damage in terms of the facade elements. We'll look at that a bit more. But there's also a theory going on that this heavy reinforced concrete grain silo in some way helped to protect sort of the western portion of Beirut. And here's where that thought comes from. Some colleagues at ARUP and also at Viper Blast did some computational fluid dynamics simulation. This is the results of their work. Computational fluid dynamics is a tool we use in various fields, civil engineering being one of them. You might think of it as something we use to model aircraft, wings and Formula One race cars, but we also don't use it in blast. And so what they've done is they've modeled the explosion and the geography of all the buildings in Beirut. And what they noticed in this video, you're going to see the pressure wave sweeping across the surrounding cityscape. Again, it propagates in that spherical pattern in all directions. The color contours give you a magnitude or a sense of the pressures. So red is the highest, blue is the lowest. What they found was this grain silo here protected or reduced the pressure on the west side of the city. And this had to do with the fact that the blast had to push past this huge obstacle, which it couldn't do, and then sweep over the top, which helped to redirect some of that energy off to the east, and again, attenuate the pressure on the one side. Before we move on to this slide, I want to explain a little bit on why the magnitude of the disaster encompassed such a large geographical area. Let's take a look at just the color contours for a moment. So the light blue color here, this is, or maybe the purple, this blue color at the boundary is about 20 kilopascals. Sorry, I'm Canadian metric system. 20 kilopascals to give you a sense. Let's say you have a window. Let's say that window is 1 meter by 1 meter, so 3 feet by 3 feet. And I apply a 20 kilopascal pressure on that. That total force that you're applying on that 1 meter by 1 meter window would be roughly equivalent to 20 NFL football players standing on top of it. Do you think likely that window is going to survive? Probably not. And that gives you a sense that even its very low pressures, a lot of the facade elements, the windows are very weak to begin with. So it really doesn't take much of a push that they're not designed to see to fail, which is why reports of damage are reported up to 2.5 miles away from the initial source of the blast. As you might imagine, the damage was evident from outer space. And so I've taken some results here from NASA and the Jet Propulsion Laboratory, and I think the University of Singapore was involved in this, and they were able to take photos of the disaster shortly thereafter from space and compare them to photos that were existing of Beirut before the blast. And by comparing the pixels and looking at what has changed in 2 photos, they were able to make some empirical observations of where the damage was most severe. And so the deeper red color is where the damage was greatest, and then yellow is less severe. And you can see this is the source of the blast. Sort of to the east and to the south was where the greatest effects were felt, and to some extent over to the west. These charts are obviously not going to tell you exactly how many buildings are damaged. They're not going to tell you how many windows are blown out, how many people are displaced, but they're going to be very useful, for example, for rescuers in being able to know where to look for perhaps people that are trapped or buildings that are come down, plan rescue strategies. So it's a really amazing technology, things that I think in the last 20 years or so that have become available widely out there. That's pretty neat in this case. So sort of having a vision for sort of the overarching scope of the damage, let's start talking about structural systems, reinforced concrete. Lebanon is a high seismic region. They've been dealing with very large earthquakes for a long time. So they're familiar with construction practices to try to prevent damage during earthquakes. They use reinforced concrete quite a bit, and what they observed, the reports seem to indicate that the reinforced concrete buildings performed really well from a structural perspective. So the beams and the columns and the slabs generally had low damage, minimal cracking, or no damage at all. The problem was the non-structural components, the cladding, the facade, the windows. And you get a sense that these things were just simply not designed in any way for this loading. And you get a sense that, entire buildings, the faces, the fronts are all just completely ripped off. So structures themselves that are reinforced concrete did well. For the most part, from what we can see, it's again, those non-structural components that were the main cause of damage and other issues. Masonry buildings. So Lebanon is closely tied with French culture and French construction practices. And so there's a lot of masonry buildings, particularly that's from what I can see that line the port area in that sort of touristy district. And so there's a lot of these pre-1950s vintage load-bearing sandstone masonry structures, absolutely beautiful historic buildings, unfortunately have no lateral load resistance. And so under blast loading and even seismic, they're very weak due to their brittle nature and no reinforcement. And the damage assessment for these buildings is very poor. So there are lots of reports of localized failure. So portions of wall just getting blown in, and then large cracks in the entire building. For example, here's a portion of the whole corner of one of these load-bearing masonry buildings coming down. And there's also, unfortunately, reports of complete collapse. So the whole building just comes down in on itself. Hopefully there was no one there at the time, but this is extremely hazardous type of construction for blast. And if it does fail, it causes a very high hazard for flying debris. So it's not just the structure coming down, but it's things coming off it that are a major problem. As you might have imagined, window facade and window damage was a major issue. You can see that here for miles, windows and things just being broken. Quite frankly, windows fail at very low pressure, and they form dangerous shards and debris. The high number of casualties is primarily because of failures of the external portions of the building. So there'll be glass injuries, there'll be blunt force injuries from projectiles flying and hitting people, as opposed to direct injuries from the blast. You can see that the facade systems, again, simply aren't designed for these high pressures. They just rip off faces of buildings, and they become flying projectiles themselves. And they also become dangerous debris that impairs, that is long lasting. So look at this, for example, this panel up here. You can imagine you're a rescuer or you're somebody on the ground. You now have to worry about pieces of building coming down and falling on your head when you're out trying to live your life and or rescue people or rebuild. So it's like mind-boggling, the scale of the problem. And there are some videos out there from home cameras showing what happens or what has happened during Beirut, people being injured by the glass. I've chosen not to show those, but instead I want to show just a video to give you a sense of what that may be like. This is from some similar blast testing. We have a mannequin here as computer. What happens when you have a window system not designed for blast? The window flies out, the frame comes at you, whatever other components, you get a sense that the computer becomes flying debris. It really comes back to that idea that we want to minimize flying debris in blast events as much as possible. And it's, I felt like a summary slide would be good here, but I just couldn't come up with one, a good enough one. It's just an absolutely, a tragedy on all levels. It really is. Switching gears a bit. And I know we're kind of running for time, so in the next 10 minutes or so, I'm hoping to wrap up, but I want to talk to you a little bit about what we're doing here at Virginia Tech to try to protect people about disasters like this one. And I want to talk to you about our shock tube research facility. If you're researching blasts and you're interested in protecting people against explosions, you need some way to generate blast energy so you can perform experiments. So you can collect data, you can validate analytical models, and there's really two ways to do that. One way is to do laboratory scale experiments that are safe and repeatable and controllable. The scale will be fairly small, so you're usually working with half scale or maybe a little bit smaller type specimens. And those are very useful. Other extreme is you'll be doing live explosive tests. Maybe you'll go to a military range or some faraway strip of land somewhere, and you'll do live explosive tests on scaled or full scale structures to establish damage patterns and failure modes at the real scale. The challenge here is balancing which of those two test programs is going to be most appropriate to collect the data that you need while still satisfying safety, economic, and practical constraints of those testing methods. At Virginia Tech, we've opted to go with sort of the laboratory scale experiments, and we've set up a blast simulator facility. So this is a question for everybody. Roberto, were you able to hear any of the audio that I had before?
No.
I will get that 1 second going.
No.
Yeah, I can do it. I got it here.
Okay.
Thank you. So I'm going to take a break and take a sip of coffee. Here's a video of a guy who knows what he's talking about, who's going to explain the shock tube facility to you in great detail.
My research looks at the effect of blast on structures, so terrorist attack, accidental explosions. And the reason why we're doing this is try to protect infrastructure and people against these extreme loads. Pressures that we generate are very similar to the kind you would get from a high explosive detonation. And this allows us to simulate the effect of blast on structural components.
We have a partnership with West Point, so we're testing some SIP panels for blast resistance. Structural insulated panel is 2 OSB face sheets that are separated by a foam core. So if you're the military, for example, you could develop these basically prefabricated barracks using this product. So we're studying how to improve the performance of these panels. It's part of a capstone project for some undergraduates, so it gives them a really hands-on experience to be able to come to Virginia Tech and use our unique blast facility to get an experience, a very hands-on experience that they wouldn't otherwise have.
So the main takeaway is students get an experience. But that's our blast facility in a nutshell. What it allows us to do is to safely, repeatably, and economically generate blast energy. So the blast energy is generated inside of this big chamber. We mount structures like shown here at the end of the chamber where we subject it to blast pressure. One of the things that it does other than research is a workforce development pipeline. So we train students working in blast and prepare them for careers in the military or research labs or even the civilian sector when they go off and move into dynamic loads, extreme loads, and that's their career choice. Shock tube itself is massive. It's 80,000 pounds. The length of the simulator is 41 feet. It's about 10 feet wide at its widest and 12 feet tall at its tallest. It's composed of a few components. We generate blast energy from the detonation of oxygen and acetylene. So we're not working with TNT, we're working with oxygen and fuel. In a detonation chamber, here's the students that are loading it into position. We detonate from a remote control station that generates a high temperature, high pressure shock front that travels down this expansion section to a test frame here at the end where we can mount these 10-foot by 10-foot targets on the front and see what happens under the blast loading. Here's an example of those SIP panels that you can see. We're an outdoor facility, which is great when the weather's nice, not so great when it's not so nice, but still, we're pretty nice weather here in Blacksburg, so we're able to test pretty year round. Students run all the tests. I'm always there to supervise, but it's hands-on. People, get to experience this thing firsthand. Here's some blast profiles, so I'll just quickly mention, remember that blast waveform is an instantaneous rise, exponential decay. The shock tube generates those types of signals, those types of pressures. In this case, this black pressure time history, this is pressure and time. Actually, no, this should be time, not impulse. This is equivalent to 350 kilogram T at 28 meters. So we can simulate some pretty large blasts, not as large as Beirut, but nonetheless, that's our unique equipment. And so in 5 minutes or so, I'll just give you a quick rundown of some of the technologies that we've developed, both here at Virginia Tech and that I've worked on previously. Doors are a major problem. Much like facades and windows, they can become flying debris hazards. They can also open during the blast event. So what we can do is we take blast resistant doors, we install them at the front of the shock tube and subject them to blast loading. So in this video, it's a slow motion video. You see a flash of light under the door, and then that's the shock, the detonation occurring, the door deforms outwards. You can see there's insulation coming out the bottom. The door is permanently damaged. If you see the latching and locking hardware is all deformed over here. So we break things, we sort of go through and we do a forensic analysis of how they failed. We look at welds, look at deformations in members. We use that information to improve their performance. We can also test concrete members. So although concrete tends to have done well in Beirut, that's not always the case, particularly under a close-in type blast. So when we test concrete members, we usually use other devices to transfer the pressure onto the member. But you can see this would be a slow motion video of a concrete beam being subjected to blast. So you saw that flash of light, which is a detonation, and then the pressure wave striking the test system and the specimen deforming outwards, and then concrete particles flying off. So we're able to instrument these specimens with a variety of sensors, displacement transducers, things like that. And students do all of this work. I mean, I check to make sure everything's right, but students do the work, which is great. Pretty strong team out at the lab. We can test columns. So this is at a previous lab. Columns hold up the building. So we obviously don't want columns to fail. If columns fail during a blast event, you can imagine what happens to the structure. So we're able to test structures to their extremes. In this column, we get what's known as a collapse mechanism form. If you enroll and you get into structural engineering, these are plastic hinges at these 3 locations that have formed where we've crushed all the concrete, we've yielded and ruptured the steel. We want to avoid this as much as possible. Some of the strategies that we might take to do that is to induce ductile detailing. So I'm going to skip this slide because this is kind of more of the same, but one of the strategies in blast that we would do to impart good characteristics is to design members as if they were going to be subjected to strong ground shaking, earthquakes. And so seismic detailing, things like very closely spaced ties to provide confinement to concrete to resist compression bar buckling, as well as increased shear capacity is beneficial. Here's an example of a column You can see the ties are really close. Here the ties are very far. The damage is much greatly reduced if you have seismic detailing. If you have a member that is not designed properly, you can retrofit. You can enhance its performance after it's been constructed. Some of the technologies that we look at to achieve that is going to be fiber reinforced polymers. This is a glass or carbon or basalt fabric. It's a flexible fiber fabric that you epoxy and then wrap or extend onto the surface of steel and concrete structures to achieve the same effect as if you were designing it for seismic scenarios to begin with. So confinement, shear, bar buckling, flexible capacity, all kinds of things. It's a pretty robust retrofit technique that's used out there. It performs really well. So here's an example of a concrete wall panel that's been retrofitted with FRP. You'll notice, I'll let the video talk for itself. Notice the load hits the transfer device, the specimen starts to deform. Actually, the FRP did debond, which is a problem with that material, but we were able to anchor it properly at the top and bottom. So we're, again, we're breaking things, we're understanding them, collecting data to see, we push them to their extreme and see what's happening. I've got time for a few more slides here. Masonry was a huge problem, unreinforced masonry in the Beirut blast. There's a few strategies for dealing with that. One of them is to try to strengthen the masonry wall. One strategy we could take is to apply fiber reinforced polymers, those same sheets, glue them onto the side, the tension surface of the masonry wall, and hope that increases flexural capacity. Sometimes that's not what actually occurs. And so here you can see the FRP did great. It increased the bending strength of the wall, but then we got a shear failure. So we solved one problem and created another. So sometimes you're better off just letting the thing fail and trying to catch or collect the debris. We want to mitigate any debris, in which case we would try to use a catchment system. So this is a masonry wall that's being subjected to blast pressure. And now on the inside, the camera's on the inside of the building, we have this metal mesh drapery, almost like a chainmail armor that's at the top and bottom anchored. And you'll see the blast pressure strike the unreinforced masonry wall, opens up the mortar joints. The blocks have basically become disengaged. But because the blocks are now striking the catchment system, it redirects those blocks back outside the building. So if you were an occupant standing, right here, let's say 2 feet away from the wall, you'd probably have some hearing damage. You'd, dust yourself off, but otherwise be largely intact. Windows are a big problem, and sometimes this will be my maybe second to last technical slide. Windows are a big problem, so we may want to evaluate protection technologies. One of them are these aftermarket security systems where you can kind of somehow protect the interior from the flying glass shards. So here, this is like a set of steel Venetian blinds that'll snap closed like you have in your living room, but now they're robust, heavy metal. Here's a high-speed video of one of those systems closed. It has an anchor bar in place to try to keep it closed. And so there's a window inside of there that gets hit by the blast pressure, but then the blast pressure leaks through the window, shatters the glass, opens up or petals all of these curtains, and you get these glass particles that fly at you. And not only do you have these glass particles, you have this 5-pound bar at waist height. And so there's, testing is a great way to understand how things are performing in blast. Here's another video that I like, right? Windows are a major problem, but we have ways to retrofit them. My last technical slide of the evening is again going to be related to windows. We have an understanding from the Beirut blast and other explosions that windows are the most vulnerable components because of flying glass and other things entering the building and striking occupants. They're a significant source of secondary injuries. You can design windows, the glass itself, to be very blast resistant using laminated glass. So this is going to be 2 panes of tempered glass, so safety glass, with in the middle a polymer membrane that's very stretchy. And here's a video that we did, a test that we did at a separate shock tube of 2 windows, laminated glass windows. They weigh a few 100 pounds each. And this is their performance. The windows did extremely well because they're intact. No glass, no flying hazard in the glass sense. But unfortunately, the connections failed. And so what you ended up having is several 100 pounds of glass flying at you, which destroyed a bunch of sensors and caused massive damage in our lab. Here's a real-time video to get a sense of what we're talking about. What we found is just giving this data to manufacturers, working with them to come up with better solutions is a phenomenal Phenomenal resource and greatly helps the field. Closing thoughts. So I'm probably a bit over time, so I appreciate your patience. So I think I have just 3 categories of closing thoughts. One on the disaster. I mean, just is completely unnecessary disaster. Again, not getting into the details, the failure to follow basic storage and handling procedures for dangerous materials led to this catastrophe. But it's not a one-off is the sad thing. It's history repeating itself. And every 10 years or so, a major disaster involving ammonium nitrate seems to occur. And it's important to keep in mind the pre-existing political, economic, and health crises that are just going to magnify the medium and long-term impact and recovery for both Beirut and Lebanon. Damage to buildings and people. Well, generally buildings seem to have done fairly well. The problem is the facades. And that's just something this isn't something that you would go out and redesign all the buildings to be blast resistant. Really, this is an explosive safety problem. There should have never been that hazard there in the first place. But we have ways, for example, for terrorist attack to have better performing facade systems. And the last one I'll note kind of touches on our current theme of the night is this blast protection. What I want to highlight is structural engineering is more than just buildings and bridges in a traditional sense. You know, blast as a field and other similar subdisciplines in extreme loading is a growing field, lots of transferable skills. You're talking about, you know, dynamics and loading and structural health and extreme materials at the extreme, and that's transferable across a range of industries from aerospace to ships to oil and gas and on you go. And so Virginia Tech civil engineering students, undergraduate, graduate, as well as faculty are working or active in this field. We think it's a pretty good place to come to if that's something that you're interested in. So with that, hopefully I didn't speak too quickly, but I'd like to thank you guys for coming out. It was a pleasure to get to talk a little bit on my research. And before I hand it back to Dr. Leon, I just want to remind you that we do have another structural engineering information session. I think a flyer was circulated. If not, mark your calendar next Wednesday, September 16th from 6:30 to 7:30. We'll be talking a panel discussion with faculty and students and maybe a few alumni just about the curriculum in structural engineering at Virginia Tech, some of the courses, career opportunities, and research. And if you want to access that, it's the same link that you used to get into this presentation. Hope to see you there. Thank you.